And now for the exciting conclusion. So what do we see?
That alpha hydrogen is going to reposition onto that negative oxygen, so it can be a good leave and then recombine.
That's a bit jumping ahead there. But we do have an alpha hydrogen. If we look at that overall structure, if it was that oxygen picking it up, we're probably looking at, was that a 7-membered ring? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. It'd be an 8-membered ring to do that intramolecularly. Not saying it's impossible, but improbable as far as kind of mechanistic designs go, typically. What you would probably see referenced in your mechanism is that your Grignard could deprotonate. It's supposed to be a green arrow. And put the electrons back on it. The order in which we do these mechanistic steps, I'm not super concerned about for this one, just because it's doing some kind of neat stuff. Officially, I think deprotonating it now is probably a bad idea. Why might we say it's a bad idea?
Oh, there's 2 negative charges. Right?
Yeah, you'd have 2 negative charges in the same molecule. So more than likely what we would do is try and protonate the oxygen first. Okay? And even then, do we need to protonate it? What functional group do we have chilling there? That's an enolate. And as we've learned from our enolates, what can they do? They can resonate / tautomerize, depending on how you want to look at that system. Okay, officially, what I'm drawing here is the resonance. Oh, sorry, I gotta take my sweet time drawing all this structure out. Oops, it's not a B. The red looks a little different today. Is that just me?
Looks the same.
Oh,
It's you.
okay. Well, that's fine. I accept. So officially what we drew there was resonance, so we should make that a resonance arrow. But then what that carbanion can do is pick up a hydrogen from somewhere in solution. Note, I'm not showing it as an acidic hydrogen necessarily. We're just picking up a hydrogen from solution. Why is it not a particularly acidic hydrogen that we're talking about?
Well, because there would be no acidic hydrogens.
Why would there be no acidic hydrogens?
Grignard would get rid of them all.
Yeah, we've got the Grignard present in solution, so the Grignard would probably quench those acidic hydrogens, nullifying their effects. But that takes us back to the carbonyl. This is where that alpha hydrogen could come into more kind of direct relevance. With that negative charge there, what we've got is an alpha hydrogen that could then attack a carbonyl. Very similar to... Say it again? So the Wittig does do a negative carbon attacking a carbonyl. Yes, in that sense that's true. But then you could say, well, why is it not the Grignard? Because the Grignard is also a negative carbon. Okay? So when we think Grignard, we're thinking negative carbon coming from magnesium. When we think Wittig, we're thinking negative carbon coming from... all except Yllid, but where I would lean towards is that phosphorus, the triphenylphosphine structure. Okay. So if we're seeing a negative carbon next to the carbonyl, we shouldn't really be referencing Wittig or Grignard. We should be referencing... It's not officially a named reaction. We have a name for it, but it's not a name after someone. Aldol.
Oh.
And because it is intramolecular, it may actually carry another name, just because if it's intramolecular, that's so different than everything else. So we got to call it something else. Twits. Okay. That can again pick up another potential mildly acidic hydrogen. That mildly acidic hydrogen could be related to, yet again, our alpha hydrogen, right? And through a sequence of steps. Do I need to show all the details of the mechanistic steps? I see a couple no's, so I'm going to accept that. Okay. Strong base can come and remove that, kick that. And we would have the final product that was, it wasn't actually shown as the final structure. That was our product number, or was it? No, it was provided. Okay, we gave that as the structure and said, this is what the actual product is, but you could go through and do the standard ester Grignard synthesis if you wanted. Okay, so this is kind of neat because you're running through the Grignard and then it initiates a whole bunch of it does some tautomerization, and then it does the aldol condensation, which gets us to our final product. Okay, with that 6-membered ring now of just carbons, we've got conjugation of the pi system, everything's grand and happy, and yay, neat. Okay, so we're running kind of an interesting secondary chemistry that requires us to kind of track the rest of those steps. Okay, which is kind of fun, or I think it's kind of fun. Kind of makes sense? So that's where that lesson is ultimately spinning out. So we run the Grignard once, tautomerize, and then aldol. Questions about that? Do you have a picture? That's fine. Okay. And then we'll also say, have a good wedding, Josie.
Oh, have a good wedding, Josie. Have a good wedding.
If anybody can hear you, everybody else said it too.
Here we go.
Okay, now we're good?
Yeah.
Okay. So now what?
Speed run challenge for today's and do the whole opening thing.
What the hell? Nope.
Starting with
Oh, yeah.
Starting with 11.
Starting with 11, huh?
You know.
Yeah, the fuck is that?
Like me and Abby figured out that 2 is the most acidic, but like 1 and 3 is kind of weird. Because they both are kind of like the same.
Yeah, I think that one's actually a typo. Because 1 and 3 do come in real close to each other. You're going to get the same stability of those products. I think the double bond was meant to be rotated 1 bond further away so that you lost that conjugation.
So do we just do 12 then?
Oh, you wanted me to actually give you answers behind it. I thought you just wanted me to speed run it and do it in my head. Because I mean, that's speed run.
Is that wrong?
That's fair, yeah.
Not wrong.
Or
Maybe
need
not
like
speed
a
run.
10-second explanation.
10-second explanation.
So I will say question 11, I do genuinely think was just a typo. That just comes from, why is it? Oh, I know why it's not doing that.
So, 2 most acidic, 1 second most acidic, 3rd least acidic.
1 and 3 are the same.
But
So
presence,
when we're looking at acidity, okay, our bottom line for looking at acidity is typically we look at the conjugate base. The more stable the conjugate base, stable conjugate base equals stronger acid. So what you should go through and do is start deprotonating and seeing what's going on. Okay, so if we deprotonate, negative, 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 and then we would try and evaluate stability. Well, they all have the same charge, so we're looking at all the same size, same electronegativity, but now we'd have to consider resonance. Okay, structure, I don't know why I got lost there, but structure 1, we could do resonance in that way, nullifying that charge would be our primary system. Structure 2, same kind of deal. We'd go in this way. Structure 3, we'd go in over here. So now what we're looking at is the stability of each of those individual conjugate bases. Okay, after having done resonance, and the resonance that we've done, you got to take it.
Look on your back. Don't call me in the middle of class like an idiot. Goodbye.
The positive, We want to neutralize positive charge first, and then we want to evaluate the stability of each of our subsequent molecules. The middle structure, benzene, the reason why this question is showing up is our fourth unit is going to be talking about the extra stability imparted on that particular structure. When we have those three pi bonds all overlapping each other and imparts an incredible amount of stability, which would suggest that structure 2 is going to generate the most stable conjugate base, therefore is the strongest acid. If we go through and look at structure 1 versus 3, they're identical. All they are is a different rotation behind it. Okay? This is why what I am postulating is that theoretically what I had intended to do, either I or the person who wrote the question, it was probably me based on looking at these structures, was the double bond should have been offset by 1, thereby preventing that extra resonance capability. Make sense? All right. So the way it was originally presented, we don't have a clean answer. It's just the way it is. Okay? That would be one that more than likely, when the exam came back, I'd get a weird response system. So I go through and look at all the output data from it, and it would probably tell me that people were effectively guessing on this question. And I'd pull it up and look at it and be like, why are you guessing? And I'd be like, oh, shit. That's why you're guessing, because you couldn't differentiate between those answers, and therefore...
Wouldn't it just make B and D just functionally correct?
They would both be functionally correct, but on a Scantron, only one of them is correct. So what I would be seeing is half the class is getting it right, half the class is getting it wrong. And additionally, a weird distribution on secondary statistics that I also run on it. Okay. And even then, if it didn't get caught theoretically, this is one of the reasons why you're asked to review your exams, is to come back and be like, I don't understand why this is wrong. And then I'd go through it and be like, oh, shit, yeah, that's a problem. Okay, so typos invariably happen. You have to be a good student as well as your instructor being a good instructor to catch those typos. Okay. 2, speed run. Yes, I can go through and do it all, except that the whole point of the open exam is that what I'm providing feedback on is something that's written there, i.e. feedback. Okay, which is great. We can do a speed run to the boards. Question 12.
The one that we just answered?
12. No, we answered 11.
Oh, yeah. Okay.
And while you're drawing up structures, because that doesn't require a lot of thought, I'll talk through this a little bit. When we rank acidity, what do we evaluate? We look to the stable conjugate base. We look at the conjugate base because the electrons become obvious, okay, or more obvious when we're looking at our conjugate base. We can see those electrons and how they potentially move around. When we move to ranking base strength, should we look at the conjugate acid?
No, you should look at the base.
You should look at the base. The whole point of bases is they donate electrons. So you're trying to find electrons. So what your focal point is will change because the definition of what you're looking at changes. Okay? So it is probably best to keep your focus on the base itself and say what makes it basic and evaluate that piece to make your comparisons. So when we're going through and looking at our structures, what we had to first establish was where were our electrons that were acting as the base. So it took us a bit, but we nailed down that we should be looking at the nitrogen acting as our base. Then we played around with it a little bit and noticed that 1 and 3 have resonance abilities, okay, whereas 2 did not have resonance. Okay, so if we're using the charge, size, electronegativity, all atom effects are the same. We don't care. We move into just resonance. Okay, 2 doesn't have resonance. Resonance causes the electrons to move into the structure. For a base to react, the electrons must go out of the structure. So resonance in this case weakens the strength of the base. Cool? That puts 2 as the highest, or the most basic. Yes, lovely. But now we're set within 1 and 3. Cool, which is one of our answer choices. So we have to nuance between 1 and 3. So what do we need to look at?
The amount of resonance, which is kind of hard to say because it's not necessarily quantifiable, but like that one's able to like resonate a hell of a lot more times than one.
Okay, I accept that.
Or are we looking just at the ability of resonance of just nitrogen? So it has to, if it has like another part to resonate, then it will be more stable.
Yeah, 'cause it's
Okay.
conjugate.
We can just move it back to that bond.
Yeah, exactly.
So they just
The
basically.
more space that the electron has to be somewhere else, it's more likely to be somewhere else than where it needs to be.
So all we're doing is looking at the amount of resonance?
If resonance isn't working as an argument, we can move down to induction.
But are your resonance arguments equivalent? No.
Why not?
Okay, yeah, why not? Why are the resonance arguments not equivalent?
Well, they don't have the exact same resonance. Like,
You need to elaborate, yeah.
This one's-
one does at one time, and 3 does it, has conjugate resonance.
So we could look at continued resonance in 3.
And conjugation makes it more
Three
stable.
pulls electrons into the system and it stays in the system, while this one forces electrons out onto the oxygen, making that one basic.
In and out is just an artifact of the shape of the molecule.
Okay,
Sorry.
fair enough.
Well, it's like, this one can go that way. It can also go this way, and then this one move, you know.
Can you compare the stability of your resonance structure for 1 and the stability of your resonance structure for 3? Yeah, they're both drawn. Compare their stabilities.
Negative oxygen versus negative carbon, negative oxygen wins, it's more stable.
Wait, but
Oh,
we're looking-
snap!
Wait, but aren't we looking for it to be more unstable? So that it'll actually act as a base, or?
So it depends how you want to answer the question, okay? And all you have to do would be flip Abby's argument on the other end and just say, well, it's a negative carbon that's more unstable than the oxygen, okay? But apply that now back through your system. Which of those is going to result in better resonance, structure 1 or structure 3?
Structure one,
Because,
because,
Oxygen handles the negative
Electrons
charge
better
better
than
than
carbon.
negative carbon.
okay, so if structure 1 has better resonance, we're effectively saying 1 has resonance and 3
Doesn't-
does not, which means,
three
Three
is the
should-
strongest base?
3 is second strongest.
careful, it's not strongest,
Oh, sorry,
it's
second
only
strongest.
stronger
Then
than 1.
Wow.
So it's 2, 3, 1.
Isn't that wild?
Is there
It
a
always
point,
comes back to bases.
is there like a point where if it has so much resonance that negative carbon would be preferred over the negative oxygen? I mean, it's kind of
So
a-
what you're asking for are exceptions. Sulfuric acid versus, oh, let's just go all in. H3O plus. Sulfuric acid is H plus, H3O plus is H plus. Sulfuric acid would be HSO4 minus. Other one would be H2O. Which one's the stronger acid, H2SO4 or H3O plus?
H2SO4.
It would be
Because it
H2O.
literally has acid in the name.
No, it would be H2O. It would be the H3O plus would be the stronger acid.
Why is the H3O plus the stronger acid?
Oxygen is neutral versus being negative.
Because the oxygen is neutral versus the sulfate being charged. So we would say based off of charge that H3O plus is the stronger acid. What is the pKa of H3O plus? Negative 1.5. Ah, it's pretty flippin' acidic. That's a low number.
What about
What about
sulfuric acid?
Negative 7.
Oh, what the fuck?
Because it has acid in the name.
I don't know that I would go that route for this particular one.
So
So are there exceptions? Yes, there's exceptions. You can run into scenarios where there's enough of lower effect things that overcome the higher level or higher order things. The same thing applied with intermolecular forces. Okay? If I look at water versus naphthalene, I know nobody knows the structure of naphthalene. Well, maybe some of you do. I don't know.
Never even heard of it before.
There's naphthalene. You have heard of it before you've worked with it.
What?
Yes. Versus water.
Oh, of course you remember.
Which one would you expect to be more solid? Because
Smaller molecule with
smaller is a dangerous word to throw in there.
molecule.
Which one would we expect to be more solid?
The intermolecular forces.
Based off intermolecular forces. That's our highest priority thing. Yeah, intermolecular forces. Water has hydrogen bonding. Naphthalene is London dispersion forces. What's the stronger force?
Hydrogen bonding.
Hydrogen bonding, which would suggest stronger force, takes more energy to break. We would expect the water to be more solid than naphthalene. At room temperature, water is a liquid, right in the middle of the more solid ranking system. What is naphthalene? Solid.
Gas.
It's a solid. Why? Why is it a solid? It has weaker forces.
Conjugation.
It has nothing to do with conjugation, would you say?
The ring.
I'm going to say no.
Size.
It's bigger.
Is
So
that
right track, wrong direction.
Yeah, so you had the right concept of, that's why I commented on your smaller statement. Okay,
Because
it's
it's
bigger. Why does that matter?
Oh,
Bigger
the amount
means
of
more
London
surface area.
okay?
Even though it has weaker forces, there's a larger surface area for interactions. Okay, so we're looking at trying to break an ice cube versus a spaghetti strand. Well, the spaghetti strand will be easier to break. But if I've got 1,000 spaghetti strands, that becomes significantly harder to break than the ice, even though we've got a stronger interaction. That, you know what I was trying to deal with.
Yeah.
Okay, kind of makes sense? So do we encounter cases where we do get exceptions? Absolutely. Okay, we absolutely do. Okay? How are you supposed to navigate those?
Look it up.
It's one option, look it up. So you're going to encounter a couple different kind of problematic things within this. Look it up. Why would looking it up be problematic?
Because looking it up also sucks.
Opening the structure.
Not everything's consistent on it.
It should be pretty consistent. Maybe you're looking in the wrong places. Okay, so there is a challenge of what you're looking up and where you're looking it up.
I guess it depends on how you're framing it.
Are you getting tested on this?
Can't look it up on a test.
You can't look it up on a test. That's the problem with looking it up. In the real world, what would you do? You'd look it up. Yes, makes perfect sense. Okay, you would look it up. You would need to know to look it up, though. Okay, because if you look up everything, you don't get any work done. Okay, so you have to know when things are going to fall apart, or have a sixth sense about it to be like, I think this is going to break. This is going to break that rule that we talked about. Okay, so how else do you do it?
Ask you.
Sort of related to that, yeah. You should ask me or potentially listen to me, and when I say, hey, you should memorize this, why am I telling you to memorize it? It's breaking the rule set that we have to explain the vast majority of our chemistry. Are there more rules that we could use to explain it? Probably. Are those worth our time? No. Okay? And that's going to come from different instructors, different perspectives. I don't think it's worth the time to dig into all of those whys, because it's going to go beyond the scope of what we need within the class. So that brings in the next point. Okay? Should you get weird exceptions on a test?
Yes.
You shouldn't, because that then assumes that you've memorized it. And so now what you're relying on is that your instructor is cognizant of what is happening. I know, that's questionable. You have me. Okay? And chooses examples both to talk about in class and on the exam that match the content that we've been addressing and how we've been addressing it. That isn't always true. Okay? I will make mistakes, and it will for sure be cases where instructors just don't give a flying rat's ass, and they'll just throw whatever questions happen to appear in their test bank on an exam. Okay? But those are questions that you should then go back and fight about and be like, when did we talk about this? Did you provide me the tools to answer this question? And when you come back and ask me, 90% of the time, I'm like, yeah, remember how I said this? Did you do that? No, I didn't. Okay, that's fine. You don't have to do that, but I set you up with those tools for a reason so that you could get to those answers correctly. That's the intent. It's attempting to be carefully designed within the content. Make sense? Okay. It does require more effort both on the instructor and on the student part, sort of. Okay? Because what it's going to do is minimize the amount of random bullshit you have to memorize. Okay? But in lieu, you have to start to understand and process content. That's why we've also done things the exact same methodology all the way through the semester. Make sense? Good work. 13. I'm going to make 13 a little bit more difficult here. You ready?
You're gonna make it more difficult?
We don't get to see the answers.
You don't get to see the answers.
Oh.
We conveniently all have writing implements or tools. Do it on your own. Define base.
Electron donator?
Okay, an electron donator, I accept that. Particularly in this case, when you're trying to rank bases, it makes sense to go after the electrons, not after its reference to hydrogen. Okay, so what's the very first thing everybody should have done?
Recognize the electrons of the nitrogen.
You should have added the electrons to the nitrogen. Okay, those are going to be our basic electrons. Once you've identified your electrons, you can now start to go through what system?
Stability list.
Your stability list. So we can start with charge. It's the same. Size.
Same.
It's the same. Electronegativity.
Same.
Resonance. Ooh, interesting. Better to have an aha and silence from everybody else.
They both can resonate, but one has a more conjugated system than the other.
I'd argue two can't.
False. And false.
If it tries to resonate, it sees the octet on the nitrogen, so we'd have to kick it out.
False.
False?
Does
Huh?
it do like velocity or form of carbon?
Okay. So, Abby, I believe in your statement of it, if it tries to do resonance, it's going to exceed the octet on the nitrogen. I believe what resonance you're trying to do is take these electrons and go there.
Yeah.
Yeah, you're absolutely right. It would exceed the octet. That's because that was a bad resonance system. What should you have done instead?
Pull the electrons off the nitrogen? That's
Yeah.
what I did.
And if we pulled the electrons that direction, the resulting structure would have a positive charge on the nitrogen. We'd have a lone pair on that carbon. Okay? And we'd be like, I don't like that. It's a negative charge on a carbon. That's fine. Okay? But is resonance possible? Yes. What is that going to do to the base strength of that nitrogen?
It's going to be a little higher. It's going to be stronger as a base.
It's gonna be.
To act as a base, what must it do? Donate the electrons. Where is it donating the electrons to?
Inside the system.
Outside the structure. To act as a base, it must donate them out. If we have resonance, where are the electrons going?
Inside.
Inside, which means resonance in this case is going to weaken the base strength. Okay? So 2 should be a quote-unquote weaker base. Right? Until we have a legit comparison, though, we don't know whether it's weaker than something else. So we have to have the comparison. So we can bring in structure 1. In structure 1, there was reference to, well, yes, structure 1 also has resonance. And my response to that was, no. You're like, but can't I do this? Why can't I do this resonance? Why is Mike full of BS in this particular case? Because we know I'm full of BS regardless.
Oh, those double bonded systems are right by each other. I mean,
That's known as accumulating. We can technically have 2 double bonds next to each
yeah,
other.
but it's
That is fair.
unusual
It is unusual.
and not particularly stable.
It's going to be not particularly stable in this case because we would have that 2 double bond system in a 6-membered ring. That's going to be really, really challenging. It
But
never happened. That very first arrow I'll call in purple is wrong.
Why?
Does it go to the double bond and triple bond?
Nope.
And so the electrons aren't able to resonate at all in any direction?
The electrons on the nitrogen are not able to do resonance at all for that structure.
What?
The electrons on the nitrogen.
No, obviously, but I'm still not getting exactly why. I get it's not exactly stable, but getting those electrons to move around, it's not exactly unheard of to see an unstable structure as part of a resonance.
Let's just look at that 6-membered ring. Okay, we'll ignore the nitrogen for the moment. We've got that 6-membered ring. We've got those pi bonds. Those pi bonds happen because of what?
P orbitals overlap?
P orbitals overlapping. So what we're seeing is these p orbitals, and what I've attempted to do is take our 6-membered ring that was planar and swing it out towards you so that all those p orbitals are coming towards us. Or not all of them, but these bonds are coming towards you. Everyone kind of understand that? If we now look at that nitrogen, there's our nitrogen sitting in there. Where's the lone pair?
Is it going towards us?
It's coming straight out of the flipping board at you. Sorry for people at home who can't do this. Where are the p orbitals?
Up and down.
Up and down. What's the O?
Well, then it can't really.
Can't do resonance.
It can't do resonance because the orbitals don't overlap. Okay? This is an orthogonal orbital system. That, I don't know why chemists like to use that description, but I hear that one a lot. Perpendicular orbitals. That lone pair is in a perpendicular plane in the pi system. Because it's in a perpendicular plane, it cannot do resonance. Why then can the other nitrogen do resonance?
Presume.
That's in an sp3 atom, which can tweak the bond angle just enough that it can drop into alignment with the pi system, which is why we're getting electrons happening through there. Okay? That's how we're getting that overlap.
So the problem is that that nitrogen's connected to a double bond also.
Yep, in structure 1, it's because that nitrogen is sp2 hybridized. It's connected to another double bond. That forces the red lone pair out of the pi system. Because it is out of the pi system, it cannot do resonance. Structure 2 has resonance. What does that then suggest about their base strength?
That one is a stronger base and two is a weaker base.
1 is a stronger base than 2. Following the question, why?
Because it can't resonate versus.
Because it cannot resonate. What's the other possible answer?
Oh, the stability of. Oh no, that's not gonna work. I was gonna say ring stability. That's kind of the opposite.
Right? And other possible answer, I think people are getting a little bit confused with that. We're saying 1 is the stronger base because it cannot resonate. The other answer is
Hybridization.
2 is the weaker base because
It can resonate.
it can resonate. There's 2 explanations that get to the same point. When we look at those multiple choice answers, we need to be looking for either of those 2 systems. Both answers should not be there, okay? But that's what we would have to be picking out. Does that make sense? Okay? And that becomes challenging because we've got one over the other, and depending on your perspective, the phrasing could get real easy to get confused within that system. So I already forgot our statements. We said 1 was more basic, didn't we?
Yeah.
So A doesn't make sense, C doesn't make sense. 2, these all say less basic, so that helps us out. So 2 is less basic because
More resonance.
it has more resonance.
But wouldn't D also be true? I don't mean.
It's not a hybridization effect, though.
I mean, if we're.
Hybridization is kind of a result of the resonance.
Oh, okay, I gotcha.
So when we're talking about a hybridization effect there, we're looking at which one's the stronger acid. The stronger acid is the alkyne because hybridization effect.
Okay, I get what you're saying.
Okay. You could also flip that back to bases. Which one's the stronger base? A or B?
B,
B, because of
hybridization effect.
it's a hybridization effect. Make sense?
It's due to the relative electronegativity. Okay, I get you now.
How many people have to take biochem? No? Yes? 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 And you don't have to take it? Oh, that's right. You're chemi, right?
Yeah, no.
Yeah. So this would be a fun question for you. Because guess where you're going to see this question?
In biochem,
Yeah, in biochem.
at a low pH.
You'll see it actually significantly worse than you'll see it here.
Is almost a good shot.
Then I'll show it. 'Cause I don't know that I've done it. I think I've probably done a demonstration in this class.
Have you done biochem?
Have I? Yeah. I have my master's in biochem. Or bachelor's? Bachelor's. Yeah. The masters aren't really in anything, but my bachelor's degree is biochemistry, and I took a bunch of biochemistry classes in my master's programs too. And I taught biochem here for 4 semesters, partly. It's probably more along the lines of I don't know the content well enough. Or I know it so well that the application part becomes obnoxious with the content of the class. Personally, to that question, as we kind of sidestep the question that's up here, nice. Yes, I find it significantly harder than biochem because my memory sucks. And most students find biochem to be easier because all you've got to do is memorize a couple key facts. And by a couple key facts, every test is filled with things to memorize. And as long as you've memorized them, you're fine. Okay. Here, I could go through, and this is one of those questions that it becomes harder on, and people struggle with this kind of question in biochem. But effectively what biochem says is, here's this structure, at this pH it's this, at this pH it's this, at this pH it's this. So what do? You memorize those. When you get to the exam, what are you going to see? That exact same structure with one of those pHs. Okay? Whereas OChem goes through and says, well, what if I do this? Now what happens with pHs? Okay? Does that have the potential to change? Yeah, it does. Okay? So we make subtle changes to the structure, and that changes everybody's perception on the overall compound. Okay? Or OChem takes it a step further, and we do things kind of like this. Oh, can't do that. That was a bad idea. Oh my God, I can't answer this question. The stuff that I drew on there has no bearing whatsoever to the question. Right? But you see this giant piece and you go, oh my God, I can't understand that because there's this new giant piece that I've never seen before. It was irrelevant. Okay? How do I know it's irrelevant? What is pH talking about?
Acidity.
Acidity. The new pieces that I drew on there, are any of those acidic? No. So they're 100% irrelevant to the overall question. Okay?
I mean, those carbons are slightly acidic, but
Okay, which does bring in an interesting question. This is where we would need to know information about pKa's. Okay, so if we're looking at a pH of 1, okay, so we can do this the painful way first. Okay, pH of 1 is what? Okay, this is acidic. Okay, that works. What is the pKa of a carboxylic acid? It's about 4.
Let's go.
What is the pKa of this carboxylic acid?
Is it not 4?
It's not 4.
Oh, it's closer to the nitrogen, so wouldn't it be greater?
If it's closer to the nitrogen, what does that do to its acidity?
Raises it.
It makes it more acidic because the nitrogen is electronegative, but we have an inductive effect on the purple.
Oh, it's never induction, says Mike. And yet here
One
you
case.
are on the exam,
Purple.
open exam.
The purple one should then be more acidic, which means what happens to its pKa?
Lowers.
It goes lower, and so we have to remember our whole inverses with our pKa's. The pKa of that one is sitting around, oops, where's my pen? About 2. And then this one is extra gross, and we'll get it to that. What's the pKa of that nitrogen? What?
I was like, is it like a negative number?
No, it's not a negative number.
I feel like it's closer to neutrality.
It's about 9, and that's insanely misleading, but we'll come back to that in a second.
Does that mean it's acidic or basic or?
9 is higher than your, and actually pKa does not make it acidic or basic. Okay, if we have a pKa of 9,
Oh, it's exclusively.
it's still referencing its acidity. But what does the nitrogen act as?
Base.
It is a base. Okay, but the pKa is a 9, and a pKa of 9 is still acidic. Okay, at least in the sense of organic chemistry. It becomes a little bit weird when you shift into biochem. So ultimately, what are we trying to figure out? We want to know the charge on this molecule. Okay, so let's take a look just at the red one. Okay, do we know a relationship between pH and pKa? No? Okay, that's fine. Do we know what a Ka is?
Stuff.
Make me remember Gen Chem stuff that I don't want to remember.
Right? So when we're talking about our pKa, we're in reference to the negative log of our Ka. The Ka is our reactant, the carboxylic acid, turning into the products where it's donated the hydrogen. Okay? So if we're looking at a Ka, that's products, H plus, over, whoops, there's an O minus, over reactants. God, come on. COOH. Yeah, that's our Ka. What was a pKa? That's right, the negative log. So if I want to bring pKa into this, I have to take the
Negative 1.
negative log of
That.
both sides of the equation.
Oh, so then they.
Right? Plus the log of COOH. I think I did that mathematical equality right. Okay? Because it's in the denominator, I can swing it up into the numerator, but I do the negative of it, which I think makes it positive. I don't know. There's pluses and minuses. Okay? This should look vaguely familiar because you should have theoretically have seen this in second semester.
Yeah.
We do some other manipulations with this. What are the other manipulations we do? What's the negative log of the Ka?
That's pKa?
That's pKa. What's the negative log of H plus?
Oh, fucking no.
Am I supposed to know that?
Motherfucker. Really? You guys don't remember the negative log of the H plus concentration?
No, it's been like a year, man.
Just H.
It's the fucking pH, guys.
Oh.
Oh.
Equals pH minus log of the rest of it. Dude, you were talking about how you don't remember shit, and then you're talking about you don't remember this?
Touche.
Isn't there like a pKa, but it's for base alkalinity?
You can do pKb's too.
Yeah.
Okay? And so you get this big old nasty expression, okay, which eventually turns into something that's sometimes written like this, pH equals pKa. I'm going to get it wrong. Does that look familiar? Vaguely? It's the Henderson-Hasselbalch equation. If you're in biochem, that's what we just walked through was effectively the derivation of it. I screwed up signs right and left for the record.
So it's the
Okay.
conjugate base over
but-
the acid?
I don't remember.
Oh, yeah? You don't remember the Henderson-Hasselbalch equation?
but I know how to figure out what it is. Because it's either the conjugate base over the acid, where it's a plus here, or it's a minus. Because that's how it flips. So I don't really remember. But we'll see what happens here in a second.
No, wouldn't it be minus? Because if pKa, yeah, it would be minus.
We'll find out here in a second.
Is all this
It's
even necessary?
Okay.
This is definitely minus.
So what this is going to come down to is now at a low pH of 1, what is the likely charge on aspartic acid? So now that we have this equation, okay, if we're at a pH of 1, we'll see how badly I did this equation, equals, well, the pKa for our acid was 4.
You're right.
I'm right? You looked it up? I would love to say that was because I'm genius. It's 50-50 luck. Guaranteed. 100% of the way. Okay? So we just plug that in. So we could now go through and rearrange this, and we would get A minus over HA equals
The negative log of negative 3.
10 to the negative 3, the anti-log, so
Oh,
I could
anti.
kill the log. Okay, and what does 10 to the negative 3 mean? Is that a big number or a small number?
Small number.
Small number. What does that mean about the amount of A minus to HA?
Small.
Very small A minus, lots of
Very
HA. Which means when I go back to this structure at a pH of 1, which structure do I have? HA or A minus?
You have the HA. So
I have the HA, which means it stays COOH.
So it's, so it's just plus 1. That's the ultimate charge. Oh.
What is the charge on COOH? It's neutral.
Yep.
It has no charge.
Yeah.
So now what I would go through and do is I would repeat this calculation with the other acidic functional groups. Okay? And what we would find, which maybe is what you just ran through in your head, is that 2 is going to generate something else that's going to be a negative, right? 1, 2, the 2 is going to be a negative. We're going to get protonated state. So we'll get the protonated state for our COOH. If we hit a 9 here, though, and we plug in the 9, when we come across, we're going to get a power of 10 to the 8th, which means
A lot of.
a lot of the conjugate base, or sorry, a lot of the conjugate,
Oh, God, that's.
I can't do math right. I'll write that down.
It's.
Come on here. 9. Do we get 9?
Is this actually how we're supposed to do
No, wait, isn't this the base form, the basic form of it right now? Or, because doesn't that act as a base? So then, would it be a lot of HA, thus you would add a hydrogen to that nitrogen?
Oh, sorry, there's where it is. So we look at this. If we're at a negative 9, we get a lot of the acid form, right?
Yeah.
What is the acid form for the nitrogen?
H3.
H3 plus.
Thus giving you a single positive charge.
That's where the positive is. Okay? So do you have to do this to process all the way through it? Yeah, no.
I mean,
Okay.
it's an acidic environment. Acids aren't going to act as an acid in an acidic environment because everything's an acid in an acidic environment. A base
So
is gonna
we
act
can
as-
run some intuition aspects behind it. Okay. The other thing you can do is you can memorize the relationship between your pH and your pKa. If the pH is greater than your pKa, you're in a more basic environment because the pH is larger than your pKa. If you're in a more basic environment, you should be in the A minus state. Okay. If your pH is lower than your pKa, you should be in the acidic state. What's the part that becomes tricky? Well, carboxylic acids, the acidic state is relatively obvious. It's HA. The amine starts in its basic state. So you have to know the protonated and deprotonated states. So if you've got this memorized, fucking hell, man. Okay. You can then figure out your different protonated and deprotonated states. Okay. What Anthony did go through and do was start to go through and do effectively this. Well, if it's a pH of 1, it's really, really, really acidic, which means I should protonate everything. Fair enough. What if it's a pH of 7?
Yeah, maybe.
Okay, so now we run into a little bit of a gray area, but this system fixes it. Okay, pH of 7, Okay? If I look at the 2, if I'm a pH of 7, is greater than the pKa, which means what's the protonation state for the purple one?
The carboxylate.
Yep, it would be negative. For the red one, it would be? For the green one, it would be? The pH, if we're at a pH of 7, that's less than the pKa. It needs to be the protonated state. So the protonated state would be positive. What's the overall charge on the molecule? -1. That's now my charge for that particular amino acid. Okay? Why does this become challenging in biochem? Oh, done. Look at that. We were done. But we're going to talk about it anyway.
They deal with giant structures.
Most of them
Comparatively-
aren't that giant.
Comparatively giant compared to what we work with.
But if we look at this structure, right? How many people have taken any biology classes? Ooh, okay, a couple people. You're on the bubble. What amino acid is this? It's not that hard. It's aspartic acid. It's sitting up there. Okay, but aspartic acid. Okay, biochemists are just as lazy as organic chemists. We don't like dealing with names, so what do we come up with? They created an abbreviation. Okay, so we could create an abbreviation for this, and we could call it, I think this one is actually obvious. It's ASP. I'm not positive on that. Okay, but dude, 3 letters? Come on. Can't I shorten that even further? No, that's arginine. A is alanine.
AS?
It's a 1-letter code. I don't remember what it is. Shit. It's a code.
It's a 1.
But y'all don't know what it is, right? Cool. We're going to say it's K. So what you could get on a test instead of this question would be, what is the charge on K? What do you now have to know? What is K? K is aspartic acid. The structure of aspartic acid had these functional groups. Those functional groups have pKa's. Those pKa's at this pH means this. You'd be like, God, that's awful. I wouldn't have to deal with that. Okay? Except it gets worse. Because how many amino acids are there?
20.
There are 20 amino acids. Okay? And what do amino acids do?
All different things.
They come together to make proteins. Okay? And just like in organic chemistry, we make products so that we can separate them away from the reagents. Well, guess what happens in biochem? We need to separate those individual materials away from each other. So we have to come up with separation techniques. One of the separation techniques we can do is change the charge on the individual proteins. And when the charge changes, I can now separate it away from other proteins with different charges. How do I change the charge? Play with the pH. Okay? But then this means I have to be able to predict what charge would be on the protein that I'm desiring. Okay? But the protein has a whole bunch of amino acids in it. So I would look at that protein code, and I don't want to write out all the freaking names, because if I write out serine, histidine,
No, one with a V.
isoleucine, okay, threonine. Okay, this would be really long. I don't want to deal with that. That's way too many letters. So what would I write out instead?
S-A.
You know your codes, don't you?
I mean, it's pretty obvious.
Oh, wow. Shit.
And what
Shitty
you would be
scares.
given is say, here's a protein. What's its charge at pH 4?
Which protein is shitty scary?
This is a protein. That's serine, that's histidine, isoleucine, threonine, tyrosine, cyranine, cytosine, alanine,
Oh,
arginine, tyrosine. Since you guys don't know, it doesn't matter, right? Someone online is like, that little guy got that one wrong. Okay? So what you would have to know is looking at that amino acid sequence, you would have to know that there's an R group coming off of that. And that R group has a pKa of... And you would have to know, because it's an amino acid, at the beginning of this, you have the nitrogen, the amino side. But the acid side of our serine is dug into the histidine. So I don't have that one anymore. So I don't have to worry about it. I really just have to worry about all the R groups. But the very last one also has an acid hanging out. So what I would do, you're good.
Yeah, no, I have an appointment. I can't-
Yeah, you're fine. You would have to go through and evaluate the pKa's of each of those individual systems at that particular pH to determine what the charge was on the overall protein. Hooray! Okay. This one's pretty boring because I think only one of those, maybe two of them, have pKa's that are relevant to biochemistry. Okay? And that relevant to biochemistry becomes important because the only thing we really care about is what it would be in a solution we're working with. But what solvent do we work with in biochemistry? Water. We only use water because that's the solvent in biochemistry. So all of our systems are water-based. So the pKa's that are really only relevant run 0 to 12. And that's about it. We don't care about pKa's for anything else. So if we looked at, I think alanine is the CH3. I always get alanine and glycine, I think, mixed up. Okay, CH3, there is a pKa for CH3. It's like 50. But that's not biologically relevant because I can't put a base in that's strong enough to deprotonate that. So I don't worry about it. So when you go through and memorize your amino acids, you typically also go through and memorize the ones that have active side chains for acids and bases. Okay? Which is neat. And shitty scary all at the same time. But that's how it works.